We've made it to Module 3, Lesson 4, Confidence Intervals for Proportions. Let's start this one with an example. Consider this. Your local newspaper polls a random sample of 300 voters, finding that 160 will say yes when they vote for the upcoming school budget. So your paper has decided to poll a subset of your voting population there in the community in order to get a good idea of how people are going to vote when the upcoming school budget is voted upon. So you can see we're interested in what the sample proportion is. What is p hat? P hat is simply those who said yes divided by the total number that they surveyed. 160 divided by 300, which is roughly 0.53, or we could say 53%. The paper's aim in doing this is trying to use this value, again, to estimate how all voters will vote, the population proportion here. And this is a common technique used with groups wanting to know a population proportion here. They're interested in that, and they want to use a sample in order to estimate it. What we have to consider, again, is if they interviewed a different 300 voters, still randomly selected, but different individuals, they might not always get the same result. We would imagine that each sample of size 300 would give us slightly different or slightly varying results. We acknowledge that this variability exists, and we know that our estimate of 0.53 is just that, an estimate, and we want to incorporate the variability. So we're going to try to create a range of feasible values rather than just one number. Here's how we're going to do it. The first thing we need to do to make sure that we can compute this range is to make sure a few assumptions are met. The first thing we want to see if it's true is if the sample was a simple random sample, or we might just say a random sample. And we saw that the paper did choose a random sample. Next, we want to make sure the conditions for the binomial distribution are satisfied. Well, let's see if we can recall those. We want to make sure we have a two-sided outcome. Yes, we have that. The voters are either going to vote yes or no. The second one is that we have a fixed number of trials. Yes, the paper decided to interview only 300 people, so we have a fixed number of individuals. We want to make sure the trials are independent. In other words, each person's vote is independent of the next. I think that's easy to assume. And lastly, that the probability of a success remains constant from voter to voter. And I think we can assume that as well. The last assumption here we need to make is that the successes were at least 10 and the failures were at least 10. That is, we had at least 10 people that said yes and at least 10 people that will say no. If these aren't met, then we have to use an approach to do this. But in our case it was, so these all were met. So basically what this does is give us permission to use our normal model, our bell curve, to address the situation. This bell curve is going to help us create this interval or range of values. So here is our bell curve that we know we are allowed to use to solve this problem. As you can see, we have it centered about p hat, our sample proportion. Recall our sample proportion was 0.53. Now typically we would take our bell curve and center it about the population proportion, just plain p. But you know, we don't know that value in this problem, so we will take our distribution and center it around our sample proportion. Now oftentimes you've seen me after I've created this bell curve and found the center. I want to find the value that I've computed over here, which is going to be a standard deviation. In other words, it's going to help us determine how skinny or how wide our bell curve will be. Our standard deviation, which actually I'm going to call standard error with this problem, is the square root of p hat times q hat divided by n. Now, the reason we're calling this standard error rather than standard deviation is because we don't know the value of p and q, and we're using p hat and q hat as sort of a stand-in for them. So it goes from being standard deviation to standard error. Now, we plug in the values we know. We have 0.53 for p hat and 0.47, that is the proportion of people that will say no, divided by the total number of people, 300. If you put that in your calculator, you can pause the video and try this, you will get approximately 0.03. Now I'm going to take that standard error and label the tick marks that are to the right, adding 0.03 at each hash mark. And likewise, I'll do that for the left. So we get a good idea of the center of our distribution and the range and spread of values as we go from right to left. Now recall, we used something called the 68, 95, 99.7 rule early on in the course. And if we go out 2 standard deviations, or in our case 2 standard errors in each direction, that'll capture 95% of the curve. So what this is telling us is that we are 95% confident that the true proportion of all voters that are going to vote yes on the upcoming budget is between 0.47 and 0.59, roughly between 47% and 59%. We're 95% confident that the true proportion, that is P, is somewhere between that range of values. So notice we aren't necessarily looking right at the 53% anymore. We're widening our scope, kind of like creating a net. And we think that it's the true proportion of all voters, the true population, is somewhere between these two values. Now this is called a confidence interval. And a confidence interval essentially is made up of a point estimate that's in the middle, that's our p hat, and we're going to go to the right a bit, and we're going to journey to the left a bit. And how far we go is called a margin of error. Now this might be a word you've seen before or heard before in the news, or when you're looking at a newspaper or a magazine article when they're polling people. This is called our margin of error. It's what we consider the maximum likely distance between the point estimate and P, or in our case the population proportion. You can see we're going to reach out to the right. We're going to go as far as this value here, which we call the upper confidence limit. I'm going to go to the left and go as far as this value to the left, which is called the lower confidence limit. So a confidence interval is essentially a point estimate, that one number you get from your survey, plus or minus margin of error. We can even write it in more of a symbolic terms according to what we're working on. P hat plus or minus E. E for margin of error. Here it is again. Let's kind of expand upon this. This is the concept. This is specifically what we just did in our last problem. We took the sample proportion and we added, subtracted approximately 2 standard errors. Remember, we calculated this with the bell curve. A general confidence interval, now this is a 95% one, is essentially this here. A general confidence interval, all I've done in this case is trade out the 2 for a z-value. We call it z star, a critical value. P hat plus or minus a multiplier here called a critical value times the standard error. So what this will allow us to do is change our confidence. Perhaps you might want to do a 90% confidence interval or a 99% confidence interval. These are all very popular confidence intervals. All you have to do in order to change your confidence level is to alter z star. Z star is for each of these very common confidence intervals listed here to the right. Notice here for a 95% confidence interval, one would use 1.96. We used 2 earlier in sort of an oversimplification of what we're doing, but a more appropriate value, a more exact value, is 1.96. That is, 95% of the values will be within 1.96 standard deviations or standard errors. We weren't lying to you earlier. We were just doing a wee bit of rounding, calling 1.962. For the rest of this module and the rest of the course, we will now begin to use 1.96. So, what if our journalist made a headline that read, "School budget will pass"? It might look like something below. How comfortable are you with this headline? I know our sample had more than half the individuals say yes, but this doesn't necessarily guarantee that this measure is going to pass on the day that they vote. You see, our true population proportion, that is the proportion that will say yes in our entire voting public, can be anywhere inside of this interval. We don't know where it is. Now, p-hat by design is in the middle. That's what our sample said. But our true opinion of all voters is we believe we're 95% confident it's in this range of values. Now, it could be on the right side of this interval, or it could be possibly to the left. We don't know. What we do know is our process that we use to create this interval is successful in capturing p 95% of the time. So if our p is indeed on the far left of this confidence interval, then the true proportion that will vote yes could be less than 50%, and the measure wouldn't pass. So we have to be cautious. When we're looking at information, we want to look beyond the point estimate and consider interval estimates. This is a great approach when you're critically examining things.